Hi, my name is Rafael Pisturi. I'm a postdoctoral associate at MIT Mathematics. Thank you very much to Dr. Kojima and IEEE Photonics Boston chapter for inviting me to give this talk. My talk today is going to be about inverse design of complex meta-optics. And this work has been done in collaborations with Stephen Johnson and Zinlin at MIT, Joey Lee, and Federico Capasso at Harvard, Elias Bayati, Arka Majumba at UW, and Youssef Boué and Payal Das at MIT IBM AI Lab. So my research interests from my PhD and postdoc are as follow. During my PhD, I focused on inverse design in optics. And since my postdoctoral studies, I have started to consider neural networks and machine learning to use as a complementary tool to more traditional techniques. And to that extent, I've worked on neural surrogate models for PDEs, and in particular very interested in knowledge discovery leveraging on machine learning. And in everything I do, I'm very interested in applications, in real-world applications. And today I'm going to focus more on inverse design in optics and neural surrogates, and of course, a lot of applications. I'm going to talk about designing metasurfaces. In contrast to traditional optics, which relies on propagative properties of bulky curved lenses, metasurfaces are very thin, like of the order of the wavelength. It's also very large in diameter, thousands of wavelengths. They're usually aperiodic. They're subwavelength patterned, and they rely on scattering properties. And we want to design them to reflect or transmit light in a prescribed way. There are a lot of applications to those devices. The first that come to mind are lenses, chromatic lenses, and then work on polychromatic lenses has been done. I'm going to show some more today, where you want to correct for the chromatic aberration for a specific wavelength. You can also design the structure to have non-trivial transmitted field, like lenses with extended depth of field. And more generally, you can add those devices as a component of a bigger system that may include post-processing. And in that case, designing meta-optics would be called, together with the post-processing, would be called end-to-end optimization. I'm going to talk a little bit about it at the end of my talk. So why am I talking about design of inverse meta-optics today, and why is it a hard problem? Well, the main reason why it's a very hard problem is because those devices present two very different length scale. There is a nanoscale, which is the scale of those features that are sub-wavelength often. You can see on the top right this focus on an image of a metasurface where you can see very small features. And this macro scale, which is the diameter of this device, which is thousands of wavelengths. And so it's, you have those very complicated patterns, and you need to refine sufficiently in order to resolve the small features, but you also need to have the whole structure in memory. And so given a metasurface, one of these devices, it's already very difficult to simulate the forward problem, just to simulate the scattered field. It already requires a supercomputer scale type of resources. And so if the forward problem is already very hard, now like the problem we're trying to solve is to find the geometry parameters of this. So we want to find all the small features of the surface, and this can be parameterized with million to billion parameters, and we're not given a metasurface, so it seems even harder to do. So now let's step back a little bit and maybe think. I would like to show a big picture of what design of geometries in physics looks like, and different philosophies. And it's important for metamaterials which take their properties from their geometries. So we start with the geometry, and the geometry usually is a parameterization of the space. And you can decide to have a parameterization with as many parameters as you like, but usually there are like many parameters. It's a large-scale optimization problem, and you need to decide on how to parameterize your device. And then once you have your geometry, you need some physics. You need to be able to say something about the physical response of your geometry. And so you can have some models that are simple or more complicated or very complete physically. It can be as simple as like trying to match an ideal phase at the level of this metasurface, which definitely doesn't solve for the field everywhere, but it's a simple model. Or you could also try to solve for full Maxwell's equation, as I told you. For this type of devices, it requires a supercomputer, or at least a lot of memory. And then since it's a design problem, you have this physics, but what you care about is a goal physical property. You want maybe your metasurface to focus light on the focal spot, or you might want to bend light, or you might want to build a multiplexer which will send light of different wavelengths to different points in space. This one, I think, is an older one because really you could do that also before the computer age, where it's more like an intuitive design, a forward design. It's also known as like a heuristic-based approach or trial and error. And in this type of approach, you spend a lot of work and a lot of time at the physical model. So you want to build physical intuition and have like and understand mechanism that might like end up like doing like what you want, your goal physical property. So you build a model, you try to get a design. So that's your step one, and then you try to get a design out of it, and then you need to, of course, validate it, build it, simulate it, so that you can check that it's actually doing your target goal. And there's another way to design, which is, which requires a computer, and which is inverse design, or also known as large-scale optimization. And here you focus first on really your goal, and you make an objective function out of it, and you try to maximize it. And this is large-scale optimization, so you can maximize it with a parameterization that has many parameters, millions. I'm going to show today like a parameterization that have up to 1 billion parameters. And so here the intuition that is that, like, you know, you're not constraining with like mechanism or heuristics, and so you really let complete freedom to your algorithm, your optimization algorithm, to find a good local optimum for you. So that just wanted to do this small parenthesis. And inverse design has been used a lot in optics. Here, those are two examples from a review paper about inverse design in optics. And this here is, I think, selecting on the left, it's a paper by Jonathan Fan, and it's selecting the wavelengths and sending at different angles. And so they're optimizing for this this unit cell that is being repeated everywhere. So it's periodic, it's not aperiodic. And on the right, you have this this multiplexer from Jelena Vukovic's group that sends different wavelengths in different channels. So we could do inverse design on full, and those are inverse design on full Maxwell's equation. And you can try to do that on metasurfaces. In fact, my colleague Xin Lin, before joining the group, did exactly that, and it works. You can inverse design a metasurface, but you can see here that I was telling you the diameter of a metasurface can be thousands of wavelengths, and here it's just 23. And it's only, and the reason why is that it's tractable only for small domains, because when you do inverse design and those large scale optimization, you still need to solve for the problem multiple times. And so if you need a supercomputer and like a very expensive simulation, you just cannot scale that well. So the question is, how do you scale? Because, you know, metasurfaces are around, and so people have found solutions. And so the way people make the problem tractable is by relying on this approximation that we call a local periodic approximation. And the idea is that, so you can see this picture of a metasurface. And if you focus on those pillars, those circles in the square, so I'm focusing on it for you. You can see that, like, if you look at the center one and its neighboring ones, like they kind of have all the same radius. And so the idea of the local periodic approximation is to break the big simulation domain into smaller simulations that are tractable on a laptop. I'm gonna come back to it later, but there are two things that I want to say already about this assumption, which is central in my talk today. The first one is that it's surprisingly robust to a lack of periodicity. As you can see in this metasurface, I chose the right 9 circles that look all the same, but like you could easily find neighboring circles that do not look the same, and it still works pretty well. You can use this approximation and compare it against a full Maxwell's equation and still have like a fairly similar result. But the limit is that this approximation really breaks down when you have high incident angles. Then it doesn't work really well. And so people have used this trick really to design very big lenses. So here we can see on the left a chromatic metalens from Capasso group, and on the right we can see an achromatic metalens for 2 wavelength from Farahon's group and Caltech. And those metasurfaces were designed with this forward approach that I was telling you about, where really you have some heuristic here. You know that like the lens should have a specific phase, like the field should have a specific phase at the level of the metasurface so that it does a lens, and then you can like break down all your small features that you want to optimize, and like for each of those features at their level you want to match the phase that you need. And so you break down the big optimization problem into multiple independent optimization problem, as well as breaking down the simulation problem. Well, there are limitations to this approach. First, you're assuming that like you have constant amplitude, or you're not telling anything about the amplitude of your field. Then the second one, I think it's more subtle, but you're constraining your field everywhere above the metasurface. And if you really want to lens, for example, like what you care about is maximizing the field at a focal spot, and that's less constraining on your design problem. And the major problem is that and I'm going to talk about complex meta-optics, meaning when you have a difficult problem, when like multiple targets are involved, or when multiple wavelengths are involved, then for each wavelength, for example, you would have a different phase matching that you need to do, and then like it's a lot of work on your material to have the dispersion that you need, so that like it matches perfectly all your independent small problems. And very likely you will not find the perfect parameter that like fits all your phase demands. And then what do you do? Because you already broke down your problem into many independent sub-problems, so you cannot do any trade-offs between your choice of parameters. And so this is suboptimal. So my research question, and I hope I motivated them well enough, are the following. How do you model extreme optical devices? By this, I mean very large, aperiodic, but with like very small features. And can you do it on a laptop, or at least not requiring like a cluster or a supercomputer? And then how do you design a surface or an optical device for complex optical functionalities? So when you have more than just one requirement, how do you do inverse design when you have incomplete knowledge of the fields? Like you're lucky to know what the phase function is for a lens, but there might be some application where like we have no idea what the phase function is. So how do you do then? During the optimization, how do you create synergies across the unit cells? By this, I mean, when you cannot really match what you need for a single unit cell, how can you counterbalance with another choice of parameter so that like overall it does better? And a question that I'm not going to speak too much about today, but is how can we leverage machine learning for metasurface design? Actually, I'm gonna talk about the limit of that. First, I would like to introduce the inverse design framework for metasurfaces that we published about 3 years ago in Optics Express. And really, this tool has two components. The first one is an hybrid solver, which has a surrogate model that handles like the small features. And the second component of this hybrid model is a convolution with a Green's function, which takes care of more of the macro scale. And then the second component of this optimization tool is the large scale optimization. So let's revisit a little bit the local periodic approximation. So let's focus on, if you see my cursor, this top left metasurface that is in orange. And we want to reconstruct the field on top of this metasurface. Of course, you could try to solve for Maxwell's equation directly on this complicated metasurface, but that would be very, very intensive and expensive. Like we would use a lot of computational resources to do that. So instead, you decide to use the local periodic approximation. And so what do? Well, for each of the small features here, the feature is basically a pillar of TiO2, titanium dioxide, on top of silica, and the parameter is that you're varying the width of this pillar. So for each of the pillar, you will like simulate a small simulation with periodic boundary conditions and get the field on top of this small simulation. So this is like much smaller than this big metasurface, even though it's like zoomed in. And you can like put the field there. So for example, here I highlighted a few, we call them unit cells, those patterns, a few unit cells and the corresponding periodic boundary condition simulation to get the field on top of that. Okay. And this is like part of a bigger grand plan. Like once you have the field above the metasurface, just you can then use an equivalence principle to find the equivalent current that you can then convolve with the Green's function and get the field everywhere. So yeah, you do all those small simulations that you can do on your you do a loop, right, with all those simulations on your laptop, and you can reconstruct that way the field by stitching all those small simulations together. And then you use the equivalence principle. So starting from the right, the electric field above the metasurface. This is from the original paper in 2018, which was a solver in 2 dimensions. So it was just for the polarization with the electric field out of plane. This is equivalent to a magnetic current. And then you can use a convolution with the Green's function that links the magnetic current to the electric field out of plane. And there is a technicality here. This integral here has an infinite support because you have an infinite interface, but you can use a truncated. You can truncate this infinite support by using a windowed Green's function. Now, another thing I want to point out here is that in this integral, we're actually solving, in order to get this easy x prime, we're solving a lot of time the same small simulation problem of Maxwell's equation, but with different width of the pillar. And if we have many of them, we might need to redo those simulations like millions of times to evaluate the field. And those are small, but that adds up, right? That becomes actually the bottleneck of this type of solver. So it's tractable on a laptop, but we would want to make those small simulations that we call so many times faster. We're in luck, at least in that case. If your unit cell is subwavelength, and you're interested in some physical property in the far field, then the whole field on the dotted line can be summarized by a single complex number, which is the complex transmission coefficient, or the zeroth order Fourier coefficient of the field here. And so what you can do is, instead of solving for Maxwell's equation millions of times, you fit a surrogate model. The surrogate model is basically a very fast model that initially doesn't really know about Maxwell's equations, but you teach it to the model. So you need to fit the model first by evaluating your Maxwell's equation for many different types of many different parameters, like many different width of pillar in the case of this unit cell, for example. And then at runtime, when you use your hybrid solver, you can put Maxwell's equation aside and use your very fast surrogate solver instead. And so this bottleneck is really alleviated thanks to that, because if you get 3 orders of magnitude increase in speed there, then like you're just a 3 order of magnitudes faster. So I just want to mention that like there are, given the local periodic approximation, which I'm going to call LPA now, you can have 2 approaches. The first one, that is the last one I talked about, is this surrogate model. And that's nice because it's very fast. You can do designs pretty quickly on a laptop. And also when you do depending on the parameterization of your structure, but it can be very easy to implement fabrication constraints, because usually you don't have that many parameters. For example, here you have the width of the pillar. And so like what is the maximum feature, the minimum feature size that you can do for fabrication. And so you can easily like put bounds on like the width of this pillar in your optimization. Well, the downside though is that like you might not be using all the degrees of freedom of your surface. And so you're working with like fewer parameters. but it's very fast. Another approach is to actually keep all those simulations. So you actually solve Maxwell's equation. So it's called like an online Maxwell solver versus a surrogate model, or like an offline surrogate model. In the case of the online Maxwell solver, the good thing is that you still don't need like tons of memories, and all those small simulations, you can do them in parallel. It's an embarrassingly parallel problem. So if you have a few CPUs at hand, it's actually not that big of a deal. You can do also design in fairly quickly, leaving more degrees of freedom, doing like full topology optimization. Right now, I'm going to focus a little bit on the approach using a surrogate model, which is much faster, and so which scales very well. The first surrogate model I want to present is interpolation. You can use Chebyshev polynomials to basically interpolate what the transmission would be for your given parameters. The good thing with Chebyshev polynomials is that it has exponential convergence for smooth function. But remember that like each training point is a simulation of Maxwell's equation. So those things matter. The number of training points that you use, it really matters. One of the problems of the Chebyshev interpolation, and we'll come back to that, is that it needs a certain number of points in each direction. So by each direction, I mean for each parameter. So the number of training points that you need is exponential in the number of parameters of your surrogate model. So when you have just one parameter, that's fine. Like if it's just the width. But if you have like a parameterization of your geometry that is more complicated, and you start to have more than 5 parameters, it becomes quickly intractable. And another thing I want to point out is that for this interpolation here, we have the Chebyshev polynomials, but Chebyshev polynomials don't always do very well. They do very well when you choose the right training points. And here it is the Chebyshev points. So on the left, you can see some interpolation of a function using the Chebyshev points. And on the right, you can see the interpolation of the same function, but using linearly spaced points. And you see this very famous Runge's phenomenon, which is catastrophic for interpolation. So the choice of point matters, and I'm going to come back to it very quickly later, speaking about a project that I worked on last year. And so now that we have this hybrid solver in hand, we can compare it to brute force. And well, we're doing this big assumption that like, well, we can evaluate the field by assuming that like we have periodic boundary conditions, and that's actually not true, because sometimes like the features change, but it's still doing pretty well. So this is using the green solver is another name for this hybrid solver, and brute force is like another name for a full Maxwell's equation solver. And you can see like here a few sections to compare the two solutions, and you can see that they don't give the same solutions. They're slightly different, but where it matters, meaning this was like for lens design, and what matters is at the focal spot, like they give a fairly similar result. And the big difference is that the hybrid solver is 5 orders of magnitude faster than the brute force solver. So I mean, I could go into detail of like the brute force solver. We could maybe try to make it better, but I don't think we'll get 5 orders of magnitude out of it. So that's my point. That's the first part, a very fast hybrid solver. And the second part to do inverse design is to set it as an optimization problem. And here it is. The high level is you want to maximize, you want to find the device, so the set of parameters, the parameterization of your structure. So those could be, hundreds to billion parameters that maximizes a function of the electric field. And the electric field is, or the field in general, the electromagnetic field in general, can be computed using this local periodic approximation. And here you can be even faster if you use a surrogate model. Then you can really compute the far field quite quickly at different points. Now, if you want to compute it at many points, you still need to do this integral for each of the points of evaluation. So you don't need to compute on a grid, so that's nice. But also, usually you're interested in objective functions that just have that just need a few evaluation of the fields. You don't need evaluation everywhere. So usually you can set the problem in a way that would not constrain the field that much. And also note that here, by definition of this optimization problem, we are already coupling the choices of all the parameters P together. So we don't have the caveat of the forward method, which is solving for those parameters independently, and that cannot do trade-offs. Here are a couple example objective functions that you might be interested for a lens. Well, the first one is like, so you need to you look at a function in a far field, and you want to maximize the intensity, say at the focal spot. That would like result in a lens if it does a job well. And the second type is like, say you really want to match a specific field at the level of the metasurface. Then you can also like try to minimize the difference between like your target field and what your metasurface is actually scattering. And we're talking about large-scale optimization when you have like 100 to a billion parameters. And so the only really reasonable way to solve those type of problems is to use a gradient-based optimization technique. And that means that you need to get the gradient. Fortunately, there is a technique called adjoint method, which can give you all your partial derivative at once and at the cost of a single function evaluation. So you have one forward function evaluation and one adjoint function evaluation. You get all your gradient. So once you have the gradient, many optimization algorithms that are gradient-based could work. The one we use is this off-the-shelf NLP implementation of the conservative convex separable approximation algorithm by Christoph Swanberg. Conservative properties is kind of nice. It means that like when you have nonlinear constraint that this algorithm can handle, like the algorithm will always go through a path that will satisfy those constraints. So if you stop the optimization before it converges, you know that at least it's respecting your nonlinear constraint. And we're talking about complex meta-optics optimization. And so it means that you have constraints for multiple wavelength or multiple target points. And so often you want to do a type of robust optimization, which is called worst case optimization. So you want to find the parameterization, so all the parameters that maximize a minimum intensity, for a bandwidth, for example. And the problem is that this max-min function, the way it is not differentiable. So we cannot do large-scale optimization with the problem formulated that way. But you can use the epigraph form, which is differentiable and which basically introduces a dummy variable and puts all your goals as nonlinear constraints. So that's why you want to use an algorithm that can handle nonlinear constraints. So I want to show like a couple examples. Those are from the original paper in 2018. There are test problems really in 2D. This one was sending different wavelengths to different spatial points. This one was like anachromatic lens for red, green, and blue. And now since then we've done some experimental realization. So actually real devices that were measured and that worked. That was very exciting. So this one was a collaboration with Arka Majumdar at UW, and it's a lens with extended depth of field, which can have applications in microscopy or computational imaging. And regarding previous work, there are methods for that, like cubic phase mask, but it results in a blurry image. and larger sphere lenses, but they have limited focusing efficiency. So we wanted to try to do inverse design. And so here, the optimization problem is just to find the structure, the parameters that maximizes the minimum intensity on a line, and this really on a segment. And this segment is like this elongated focal spot that you want to have your extended depth of field on. Something to realize that you don't know the ideal phase for that. So like you cannot use the phase matching technique anyways. So you have to do some type of inverse design. And we designed here the width of a pillar of silicon nitride on top of a substrate of silicon nitride at the wavelengths of 633 nanometers. This was a 2D problem in the sense that the solver was 2D, and so it results in a cylindrical lens where like basically your optimal structure is extruded out of your screen, and it looks like that. And we could have a 3 times increase of the depth of field compared to a regular lens. So we're very happy with that. And so we can see that the experimental results match the theory very well. And this is another application I'm very excited about, and that we just posted an archive that was done with my colleague Joey Lee and Federico Capasso at Harvard. And this is a very large polychromatic lenses for visible wavelength. So here the properties that we were targeting for was polarization insensitive and having a big diameter. And previous work for like this type of applications were very limited in diameter. So it was like up to 50 microns. And the reason is that like the design approach didn't really scale well for bigger diameters, because then you have too big of a phase variation and doesn't really work. So we set it up as an optimization problem of inverse design. And well, of course, here there was a lot of legwork because now we have 3D Maxwell's equation. So we had to do that and get and now we want to find a structure that has up to 1 billion parameters that maximizes the minimum intensity for multiple wavelengths in a set of wavelengths. Okay, and here the unit cell is this like a titanium dioxide pillar. This is a top view that has like 2 parameters, a width and a length, and it's on top of silica. So here, like, yeah, we had to work on making this problem, tractable in a reasonable amount of time, and we ended up having designs within hours, so like very fast for this type of problem. And so we implemented a rotationally invariant parameter function, and so it's a huge computational cost because instead of having a two-dimensional integral for your convolution with the Green's function, now you have just a 1D integral. So that's that much faster. And so the cost goes with the diameter, proportional to the diameter. And so you can, depending on the size of the thing, like for the bigger lenses, like it took a few hours to optimize it. So the first application that I want to talk about, which is in this preprint that is an archive, is a 2 millimeter diameter lens that is polychromatic for 6 wavelengths. So polychromatic, it's like you have no chromatic aberration, so they focus on the same focal spot, and you can see that like this was fabricated. The intensity on the focal line was characterized, and it looked good. In fact, we compared it. We did it for a numerical aperture of 0.3 and another one more challenging of 0.7, and you can see that for both we're pretty close to some diffraction limit. So we got like a diffraction limited focal spot, and they all focus on the same spot, so there's no chromatic aberration. So we're very happy with that. But we continued. We did also 1 centimeter diameter lens. Now 1 centimeter is pretty cool because now you can start to have there are a lot of applications where you need this type of diameters, and like where 50 microns would be like way too small. So we're starting to have like to be in a realm where like the applications can have a big impact. And so we did also a polychromatic, so correcting for chromatic aberration for red, green, and blue. And you can see, actually now we can see a picture. We don't need a SEM image. You can see a picture of the image of the lens, and well, of course, also the SEM. And want to characterize the focal spot. If you see here, the stray ratios are all above 0.8, which technically means that it's diffraction limited. It was used for some imaging, and you don't see much blurriness, so it's doing very well. And it is achromatic. Here the length scale is in micron, but the focal length was 1.5 centimeter, right? So it's 1.5 10 to the power of 4 microns. So here we're talking about like the biggest focal shift is of 0.03% of the focal length. So we're very happy with those results. And so I just want to make sure you like, I don't want to sweep under the rug the fact that like this is like a significant conceptual advance compared to this paper from 3 years ago. Going from 2D to 3D is a lot of legwork, but also like the design, the number of degrees of freedom, it's 6 orders of magnitudes increase. It's huge, and the diameter went from like for a 2D design, like hundreds of wavelengths to like more than 10 to the power of like 10,000 wavelengths. We also had to take polarization into account. So that's also like something that's fundamentally different. And also like 3 years ago, it was like, test problems, which were nice and very encouraging, but here with like real experimental realization. Just to give you a quick, it's hard to know what 6 orders of magnitudes are. So I wanted to help you a little bit with that. Like the net worth of an average postdoc is probably like around 100K. And the net worth of like the second richest man in the world is around, $100 billion. So that's what like 6 orders of magnitude is. It's a pretty big difference, actually. I mean, I let you draw your own conclusions about choices in life and what is fairness, because like an average postdoc did maybe 10 years of university level studies, and Elon Musk I think stopped at this like this 4th year. But it's good to know this difference. I wanted to quickly talk about a few other topics today. So I mentioned that when you have you can also have a lot more degrees of freedom. So here on the left, I'm showing like those parameterized structure where you have maybe a cylinder with a radius that varies, or like a pillar that has like a length and a width that can vary, or like maybe a cross that has like a little more parameters. But you might want to also like leave like all the pixels from a top view, like all the material at each pixel like free. It's called topology optimization. In that case, of course, it would take too long to train a surrogate model. So you will have too many parameters. So you want to actually do the simulations many times. So and in that case, it's actually beneficial to, instead of having a subwavelength unit cells, to have periods that are bigger than the wavelength. So this is this is a case of online Maxwell solve for this hybrid system, and my colleague Zinlin extended the framework with local periodic approximation to topology optimization here, and this is an exciting research direction that has many new papers since. I want to also talk a little bit about neural network surrogate. Like I told you, like, well, we have a solution like when you have 1 to 4 parameters per unit cell. We have a solution when you want to give complete freedom. But is there a way to have like a fast surrogate model, like somewhere in the middle, when you have like more than 5 parameters, but like less than 1,000, And the thing is that, as I told you, the Chebyshev interpolation suffers it's called the curse of dimensionality. It needs a number of parameters that is exponential in the number of parameters, a number of training points that is exponential in the number of parameters. And so it kind of doesn't really work. But neural networks are actually working pretty well there. So a neural network is this algorithm that is like famous now, where basically you have inputs and then you do a bunch of matrix multiplications that you compose with some nonlinear activation functions, and you do that for multiple layers. That's actually a feed-forward network, which is like the one I'm talking about today, and it has a lot of practical successes. And I'm mentioning some work on neural surrogate in the literature. I want to like say a word of caution. So here are two pictures of two people who worked really hard on the physics model. So there is like James Clerk Maxwell from like he's a Scottish, and I felt obliged to also add a fellow Frenchman, André-Marie Ampère. And so there's some hype, like lots of people wanting to use neural networks in optics. But in optics, our physics model is great. I mean, it's not like we're trying to recognize faces and there's no real good model to do that. Like Maxwell's equations are really good to describe how a light behaves. And so since neural networks don't have physics in them, it's difficult to compete with those physics models. And so in general, it's just like more efficient to optimize directly with the Maxwell's equation as a PDE constraint. But there's one case where you have a competing advantage of a surrogate model, and especially with neural network. And that's when you have this reusable building block, like in our case, this like simulations with periodic boundary conditions that you're gonna reuse millions of times. And so it's worth it to spend the time training it, because then you just gain so much time at runtime. And in the case where you have many parameters, you cannot use interpolation or other traditional techniques. And in that case, actually, neural networks are a good solution. But not every problem is like that. So I just want to, and I just have a few slides left, but I want to talk about those neural network surrogate. One of the big questions about neural network surrogate, similarly to Chebyshev interpolation, is to use the right points, like to find the best points. It's very costly. It can take a long time to really train your neural network to actually be a good surrogate for Maxwell's equation. And since you only rely on it, like you don't use Maxwell's equation at optimization time, you want it to be good enough. So we want to know what is the best set of training points to increase the accuracy, and so that the neural network is good enough. And for that, we want to use feedback from the learning itself, and this is called active learning. So that's some work I did last year, and that we published in PJ Computational Materials, where basically it's an algorithm that will help you in it's called exploration exploitation trade-off. You want to explore, meaning you want to find like the points where you want to solve your Maxwell's equation to train, but you don't want to explore too much because this costs you time and computational resources. And what you really want is to be able to exploit, to really do like your optimization and like use your surrogate model millions of times. And so, for example, for this problem, which had like 10 really independent parameters in the unit cell, we managed to, for a given accuracy, reduce the need for training points by an order of magnitude compared to choosing points at random. So we're quite happy with that. And you can see also here, so this is basically the error you get for the number of points that you have. And you can see that like the more accurate you want to be, the better you're doing if you use active learning. And you can see that like interpolation is somewhere out there because it's unfortunately suffering the curse of dimensionality much more than neural networks do. So I'm gonna talk. I do have a couple more slides, but I wanted to talk about the ways forward things I'm excited about. Well, one of the thing is end-to-end inverse design. So it's like using this framework I told you, but like including something afterwards and optimizing it all together, which I'm going to tell about. I'm also interested in, like, right now the incident light is all plane waves. I'm interested in, like, having maybe incoherent incident light, and like how do you do efficient optimization with that. Another thing is I'm interested in proving that, like, what people have been using for 10 years is actually relevant. But I mean, more seriously, it's just I'm trying to find corrections to the local periodic approximation, and this correction would be useful to tell you, like, well, maybe for this application you should not be using local periodic approximation. You should use another decomposition method, and there are like other decomposition methods out there that are very useful. And I'm also excited about those neural surrogate models for physics for knowledge discovery, and also for inverse design purposes. But yeah, as I said, like, you want to use it cautiously when it's actually useful. I just want to talk about really quickly about end-to-end optimization. The end-to-end optimization is a natural extension of this inverse design principle. Really, like, what you care about instead of just a physical property is like you're using like a physical signal, a physical output, but what you really care about is the target functionality. It could be like some computational imaging or a classification problem. And it's the same idea. You want to focus on what you care about, which is here this target functionality, and optimize all your parameters together across your whole pipeline. And here it's like your geometry has some parameters, your post-processing also has some parameter, and you want to optimize them together at the same time. And why is it useful? Well, it can save you a lot of money in the end. If you want to do, for example, some imaging using like an all optical system, then you need to have a very good optical system, because you don't have like very much post-processing. You just have the detector. And so that's costly to have something well aligned and like well made and all. And it's bulky. The second way would be, well, we can also not have any optics, but then like the image on the detector like doesn't look like anything, and we need a lot of post-processing, like big algorithm to try to get it to work. And sometimes like it's too noisy, and you can actually not do the inverse problem, and you're limited. And the idea of like this end-to-end design is to basically get a little bit of both, but really get the best of both worlds, where like you don't need a lot of computation, you don't need like crazy amount of diffraction or anything, of diffractive optics, but you have a little bit of both. But since they are like optimized together, you have like synergies that make it all work at a smaller cost. So that's also quite exciting. And this is following pioneering work, by many groups. I hope this presentation was interesting to you. Thank you for listening. I wanted to acknowledge again my collaborators.
Thank you very much.
Sure.
Thank you very much for the very exciting talk, very interesting. And I know there'll be lots of questions. So if you have any questions, please write in the Q&A section, or you can raise your hand, and maybe you can ask directly by voice.
So I see a question already about validation. Sometimes the structure is really so big that you cannot really numerically validate it. So fabrication is actually the validation. In the case of, for example, the 1 centimeter, lens, we could simulate it using our hybrid solver. But really, like, the only way we had to really validate the model was to fabricate it and see that it works very well. And so what tool algorithm do you use for large structure? well, we obviously use the hybrid solver that I presented today. Can conventional semiconductor fab be used for 1 centimeter lens? Well, that's the idea, right? Like of metasurfaces, to try to use the same fabrication capabilities as the well-funded semiconductor industry. And the answer is yes, that's the goal. That's why we use this type of metasurfaces, and that's why we also include those type of fabrication constraints. Yeah. Here that it was using TiO2. So I mean, I'm not a fabrication expert, but it's definitely like the reason why it's impactful to work with metasurfaces. One of them.
Can you see the question in the Q&A?
Oh, this is the chat. Okay, now I'm looking at the Q&A.
Yes.
There's one open question. What are your thoughts on incoherent and perhaps partially incoherent sources? How would you approach the design of a meta-lens, for example? Well, that's a very good question, which I'm working on right now. Definitely, it's very expensive if you try to do it by using the plane wave basis to expand your sources. So you need a way to, in a smart way, include, incoherent light, and also, some kind of, covariance between your different sources. You need to include also the randomness. It's a very good question that I'm still working on right now, but I'm hoping to find a clever way to solve that very quickly. So that answered like the solutions of inverse design problem are frequently non-unique. How unique are the solutions in the case of inverse design of metasurfaces? That's a very good question. So in what we're talking about very large scale optimization. So you have, million to billions parameters. And so there's no way to find, a global optimum to that. So what you do is you solve for it until it converges to a local optimum. And you try that with multiple starting points, maybe, and that's how you find the best design that you can make. And then you want your best design that you can make, that you can design, to be good enough compared to criteria that you're being given by someone who's interested in this design. So that's really how it works. So yeah, the question, the answer to the question is that yes, there are like many solutions. It's not unique, and in fact, I cannot even guarantee that it's the global optimum. So yeah, I hope it answers that question. Do you see a path to application of the method presented non-rotationally symmetric 3D problems? Oh yes, in fact, I've done that already. It's just like a little longer. It's harder to scale because like already here it took a few hours. I'm pretty impatient, right? Because a few hours really is not that long. But like if you're willing to spend, days, then you can leave all your. You don't need to use the rotation, the cylinder symmetry. But that being said, something that is interesting about the fact that we use cylinder symmetry is that you can still get some degrees of freedom by sampling your cylinder symmetric function more finely than the period of your unit cell. And in that way, since you're going to evaluate your unit cell, every period, but also in different directions. It can be up to every square root of 2 times the period. And so you're just evaluating your parameter function at different points. And so you do get like a little more degrees of freedom, but it's of course like not as many as if like all the unit cells were free. I hope it answers that question. Can you elaborate on why LPA fails at a high incident angle? So I'm gonna give a physical intuition. Well, at high incident angle, the light propagates to it basically sees more unit cells, so it doesn't just care about the neighbors, it sees more of that. And like if it changes a lot, and it does, right, then your approximation becomes like not good enough. You can also, if you want a more theory-based approach, I have a paper about that. That is this paper that is based on integral methods, that will answer your question on like, well, why LPA fails. It's like this one, Perez, and Sevilla, which is a colleague of mine, and in Optics Express. It's called sideways adiabatic theorem. And we elaborate more about that there. If you optimize for 6 wavelengths, is that solution fairly good for, say, 100 wavelengths? Does interpolation work? I see. So the question here is, when you have polychromatic, so like something that works for multiple wavelengths, is it broadband? And the answer is no. If you have like a single layer metasurface like the one we optimized for, there's only so much you can do. It's a very hard problem to do broadband. And so if you don't want to do something that is like, if you want to do something that is high diameter, you can't really have broadband. You can have polychromatic for sure, and like you can do multiple wavelengths. But if you want to go broadband, I would advise to go with like multiple layers.
Okay, and we have Plamen raising the hand, so I will ask Plamen to speak. Hey, Plamen, you are okay to talk.
Yeah, I mean, if Plamen is not talking, we also have Jinsun, who asked about the number of effective degrees of freedom when you have 10 to the power of 9 parameters to optimize. So there is some work on, when you have a subwavelength unit cell, there is only so many effective degrees of freedom that you have, right? But here, we have 10 to the power of 9 unit cells. So they can all change, and so the field changes also, like when you change the parameters, so you have the same number of degrees of freedom. But in topology optimization, for example, you can, for example, say, oh, I want to leave free like each pixel, and so I have like 10,000 parameters in my subwavelength unit cell. Well, your actual degrees of freedom are not 10,000. And I would refer to you to the paper I published on active learning last year, because in this paper I didn't talk about it today, but we also got some intuition discovery from the neural network model, and basically we realized that it's much easier when to learn a surrogate model with 10 parameters when really like the radius of the design space is subwavelength, and it's much easier. And we even did a SVD on that, and we realized that there were actually, even though there were 10 parameters, there were actually only 2 effective independent parameters. So it matters a lot how big your unit cell is when you use local periodic approximation.
Okay. Any more questions? Or Plamen, would you like to speak now? Okay. If not, then I have one question That is there a rule of thumb of when APA breaks down, like let's say, 20 degrees, 30 degrees, or it's hard to generalize?
Yeah, so you said, like, is there another solution than local periodic approximation? Is that your question?
My question is there a rule of thumb of where the APA breaks down?
Yeah, I would definitely say that, 30 degrees is like is a lot. In that case, I would use another domain decomposition method. Personally, I would use something like the overlapping domain domain decomposition technique, which was developed by my colleague Zilin. And it's different from local periodic approximation. Yeah, I would say, yeah, it's hard to know exactly a number because in my application, I've stayed like fairly close to normal incidence. Like I've done up to 10 degrees, if I remember well, and this worked well, but I haven't tried 30.
Okay. And well, there's one more question from David.
Oh yeah. Did I understand? I said that. Yeah, I said that. Yeah, that's yeah. I saw that in the chat. Yes, the designs here are polychromatic in the sense that, like, they work for the wavelengths of interest. For example, like red, green, blue, or like I also showed like the 6 wavelengths, which were spaced evenly in frequency domain. And it works well around those wavelengths, but if you go smack in the middle between 2 wavelengths, you don't have focusing. Yeah, it's not broadband, it's polychromatic. I think that's the major difference in concepts between polychromatic and broadband. And again, I don't think that, like, at such large diameters, with a single layer, I don't think you can really do broadband.
Okay, thank you very much